Pluto, the bewildering planet living at the outer extents of our nearby planet group, is stirring up energy inside the infinite local area. Continuous reports demonstrate a likely encounter with Neptune, raising concerns among analysts and space fans alike. Esteemed experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the probable aftereffects of this celestial clash. But how did Pluto end up on a collision course with its faraway neighbor? And what could this endless crash mean for us here on Earth? Let us examine this unfolding event. Once remembered to be an undeniable planet, Pluto was thusly renamed as a dwarf planet because of its extraordinary orbit. Notwithstanding this change, it continues to enthrall and draw in space specialists. Continuous forecasts from unmistakable scientists highlight a pushing closeness between Pluto's orbit and that of Neptune. These experts caution against a potential collision between the two planets, representing a significant danger to Earth. Pluto's excursion around the Sun is marked by its unique attributes. Within our nearby planet group, its orbit spans an amazing 248 years, and since its discovery in 1930, Pluto still hasn't completed a full revolution, adding to its interest. The incredibly round shape of its orbit is a departure from the nearly round orbits of the major planets. Additionally, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making its way more inclined compared to other planets. One noticeable feature of Pluto's orbit is its intersection with Neptune's path. For around 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging assumptions based on their relative positions in the nearby planet group. So why hasn't a collision happened between Pluto and Neptune? The explanation lies in the gravitational forces exerted by other planets. The study of Pluto's orbit began shortly after its discovery, presenting a perplexing challenge for astronomers. Unlike most planets, whose orbits align somewhat near the ecliptic plane, Pluto's unique features include a steep inclination and an eccentric orbit. The mystery grew with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amid these complexities serves as evidence of the intricacies inherent in space mechanics. The three-body problem in space involves calculating the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem explains the complex trade of their orbits and gravitational forces. Terms like AIML, libration, and the Koi effect help unravel this celestial mystery. Astrophysicists contend that libration, responsible for maintaining planets in their orbits, plays a vital role in the Pluto-Neptune system. This term refers to the fact that when Pluto crosses Neptune's orbit, it is arranged about 90 degrees away from Neptune, effectively preventing potential collisions. Libration ensures that when Pluto approaches Neptune or other giant planets, it is primarily aligned over their orbital plane, offering an extra layer of protection against impacts. The Koi effect explains why Pluto's orbit around the Sun appears irregular but remains stable over time. Despite apparent irregularity in space, numerical simulations in the late 1980s revealed that, despite its consistent properties, Pluto's orbit is actually turbulent, with slight initial deviations leading to significant changes over long periods of time. However, Pluto's exceptional orbit maintains stability over incredibly long timescales, keeping disorder within limits. Continuous computer simulations have improved our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path near the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto's, contributes to the stability of Pluto's orbit. Moreover, Jupiter's massive gravity exerts a significant influence, while Saturn's impact, although smaller, also plays a role. Through extensive studies, scientists have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the protected and stable movement of Pluto in space for billions of years. These phenomena are crucial for maintaining the order and consistency of celestial movements in the universe. Without these mechanisms, the solar system would be prone to greater chaos, potentially leading to collisions or ejections from stable orbits, with widespread consequences for other celestial bodies. Understanding Pluto's orbit is especially significant in discussions about a potential collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of the planetary system. Pluto's case highlights how seemingly unstable orbits can achieve balance through the complex interaction of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are essential for gaining a better grasp of our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a perfect example of this unpredictability. The nature of orbital mechanics strikingly demonstrates the delicate dependence of a celestial body's path on its initial conditions. As shown in Pluto's case, even slight variations in the dwarf planet's position or speed can dramatically alter its long-term orbit. Automated simulations have been instrumental in helping scientists understand how Pluto moves in space. By making small adjustments to these simulations, space scientists can observe how even minor changes can have a massive impact on Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating aspect of Pluto's orbit. Despite factors like AIML and libration contributing to its stability, Pluto's orbit can still exhibit inconsistency. Even a small initial difference in Pluto's position or speed can lead to significant changes in its orbit over many years. Regardless, despite this inherent turmoil, Pluto's orbit remains stable for such a long time, spanning billions of years. This suggests that beneath its seemingly irregular appearance, Pluto's journey around the Sun follows a coordinated order, predicting celestial events. Predicting the future paths of celestial bodies, especially for planets like Pluto with unusual orbits, is incredibly difficult. The inherent unpredictability of these systems makes long-term forecasts uncertain. Numerical simulations help us understand and estimate the future movements of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily depend on accurate initial conditions and simulate complex interactions, where even a small error can lead to drastically different results, making precise predictions challenging. The turbulent nature of celestial orbits like Pluto's reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the planetary system. It shows how the presence and position of each planet can affect the stability and direction of other bodies in the system. Notwithstanding these complex forces, notable astrophysicists are expressing concerns about a possible collision between Pluto and Neptune. Neil deGrasse Tyson, a famous astrophysicist, offers a unique perspective on the mysteries of our planetary system, especially with respect to Pluto. Tyson, renowned for renaming Pluto as a dwarf planet rather than a full-fledged planet, shares insightful thoughts on how our understanding of celestial mechanics is constantly evolving. Tyson sees Pluto's renaming not as a demotion but as a necessary adjustment in accordance with our growing knowledge about the various objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He views the complexities of orbits like Pluto's as a testament to how much more there is to discover in space. Tyson believes that the allure of these mysteries is what makes space science so fascinating. Moreover, Tyson is aware of how space-related events and discoveries capture the public's imagination. He sees events like Pluto's renaming and its peculiar orbit as opportunities to engage the public's curiosity and interest in the universe. By discussing the dynamic and sometimes chaotic aspects of space mechanics, Tyson encourages a deeper understanding and excitement for the universe. Neil deGrasse Tyson opens a window for the general public to marvel at the wonders and mysteries of the universe. Working alongside other researchers, Tyson actively warns the public about the potential dangers of Pluto's surprising orbit. After extensive study of Pluto, he has raised concerns that the three-body problem could pose a significant threat, suggesting that a collision with Neptune might be long overdue. Furthermore, Tyson stresses how such a collision could disrupt the equilibrium of the universe and lead to catastrophic outcomes, potentially even extending to Earth. A collision between Pluto and Neptune would be a rare and devastating event in our solar system. This impact would release a massive amount of energy, likely disintegrating Pluto due to its smaller size and icy composition. Debris from the crash could spread throughout the nearby planetary group, presenting potential hazards to other planets and their moons. For Neptune, such a collision could possibly alter its atmosphere and orbit, depending on the specific details of the impact. Michio Kaku, a well-known theoretical physicist famous for his work in string theory and science communication, offers an intriguing perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide profound insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, according to Kaku, can offer valuable insights for future space missions. This knowledge can help in navigating the planetary system more effectively, anticipating potential hazards, and planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to the exploration of other celestial bodies, providing a framework for approaching and understanding distant worlds. In examining the physics of planets, Kaku often highlights the significant connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to grasp these principles at their most basic level. He suggests that considering the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also addressed the potential collision, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, providing a rare observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The impact of such a magnitude in the nearby planetary system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extreme conditions. A key focus in string theory is also the gravitational waves produced by the impact, which could provide valuable data for testing predictions of string theory related to gravity and spacetime. While the direct effect on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a significant illustration of celestial mechanics, demonstrating both stability and turbulence within our nearby planetary group. The unique features of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. The universe holds many secrets, and the three-body problem is just one of them. There are other potential disasters that researchers anticipate. While the likelihood of planets crashing in space is quite low, it is not entirely impossible. The way planetary orbits are affected by various factors, including gravitational interactions, is explained by the three-body problem. In some space systems, like TRAPPIST-1, with 7 Earth-sized planets, gravitational forces create a musical pattern known as orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, impacts are not currently occurring. Scientists closely monitor these systems to understand how planets influence each other's orbits, especially when they are in close proximity. This data helps us understand the movement of planets in space. Rogue planets, drifting through space without orbiting a star, present an additional curious element. These planets, once part of a star system, are ejected due to gravitational disturbances or other celestial events. For example, the close approach of another star or dynamic instability in other systems can cause these rogue planets to travel vast distances, potentially entering regions far from their origin.